We've now learned what a discrete random variable is, what the discrete random variable's probability distribution can look like, graph, table, and so on. And then we learned how to find the mean and standard deviation for that distribution. So we want to take a deeper dive into this expected value idea because I mentioned in the last video it's very important. So I wasn't kidding. So let's look at it some more. So the expected value is just the mean of the probability distribution. So don't get yourself bent out of shape about the terminology. But it's a mathematical way to use probabilities to determine what to expect in various situations over the long run. It's got a tremendous amount of mathematical power because probability is talking about the future, and the expected value is letting us know what to expect in that future, which is incredible because we're able to say things about the future mathematically that we couldn't do until probability and the probability distribution were invented. It allows us to say, hey, what is the best outcome? What's the expected outcome here? What do I expect for these two cancer treatments? What are my expected um, premiums for insurance policies, for example? What are my expected risks when I take this business venture versus this business venture, or when I buy this stock versus this bond? What can I expect to accrue from these two decisions, or three decisions, or four? How many children, if I have four children, how many boys can I expect? Right? It allows us to envision the future in a mathematically sound way. For games of probability and chance, of course, this is extremely important. This is what separates people that can count cards and people that are professional players from the average public. Because professional players have, if they're truly professional, they have a very good sense of what the expected values for the profits are for the game of chance that they're playing. One other comment about profit for gambling games, and we'll come back to this, is that a fair game, when a game is called fair, so it's, fair game, that means that the game has an expected value for the profit of 0 for the player or for the house, because if it's 0 for both sides. That means you don't walk away expecting to either win or lose. Now, grant you, casino games generally don't work like this because if they did, they would never have enough profit to run the casino. But nevertheless, that's the way it would work. All right, so let's look at a basic expected value problem. And I apologize, in the fall of 2015, I didn't actually put these outcomes in here at first, but now I have them. So you will learn how to calculate these in section 6.2. So if you're wondering, hey, where did these probabilities come from? I'll just make a little note here to us. The probabilities we will learn how to find in section 6.2 very quickly and easily, which is a good thing because they're actually quite tricky to find. That's why I'm just giving them to you. So 0 is not too hard. That's girl, 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 girl. If you have no boys, then you take the probability of a girl and to the 4th power. Similarly, if you have 4 boys, it's the probability of a boy to the 4th power. And we're assuming there's only 2 equally likely genders, as we typically do. We don't deal, of course, with the whole, 80% likely for a boy and etc. And we're not dealing with the transgender issue, not because it's not worthy of topic and note. It's just we're trying to do kind of a more basic problem than that is. The real kicker becomes when you start dealing with, let's say, 2 boys, because which 2 are the 2? It could be the 1st and the 4th, the 1st and the 3rd, the 1st and the 2nd, the 2nd and the 4th, the 2nd. You see what happens. And you'd have to find 6 different probabilities to be able to come up with this probability of 0.375. So what you know from chapter 5 would mean that these 3 interior probabilities are actually quite hard to find with the chapter 5 rules. But we'll learn how to find them very quickly and easily in section 6.2 with a formula. So wait for that. And your calculator, quite frankly. But in the meantime, let's find the expected value. So that was just a little side note for us. There we go. So it's the expected number of boys is the mean for x, x being the number of boys. So if you wanted, you could say this is x, right? The number of boys. There's your random variable. And all we want to do is find the mean of this distribution. I think it's pretty obvious what it is, but let me grab the calculator and find it anyway. So stat, edit, I'm going to go up and clear out these old values and type in these new values. So I'm going to type 0, 1, and so on. Oops, 0, enter, 1, enter, and so on. I'll be right back. There, they're all in there. Then I'm going to go to stat, calculate, one variable, L1 and L2, and I'll go down to calculate. And I see that the mean is 2, which should not be any shock to you because this is very much a symmetric distribution with a peak at 2, right? The highest bar would be 2, and then it would tail off towards the ends. So you're more likely, if you want to think of it this way, to have 2 boys than you are to have no boys or all 4 boys. Okay, so it would be 2. And while we're on the subject, the standard deviation was 1. Right? And again, that's happening because this is a very symmetric distribution. So I put in the standard deviation here of 1. And then what this means is if you're thinking of having 4 children, exactly 4 children in the future, you can expect 2 boys, give or take 1 boy, I guess I should say. Right? Because this is your mean, your expected value right here. And that's how many boys you would expect if you're going to have 4 children, provided all these other assumed things are true. Now think about how powerful that is. I mean, that's why when you see a family with 4 kids and all 4 of them are boys, you kind of do a double take. It's a little bit unusual to have all 4 boys or all 4 girls. It's much more likely to have some kind of mix of boy and girl. All right, now I also mentioned that this was good for insurance premiums. This is how they calculate how much they're going to charge you. So let's look at what that means. So an automobile insurance company has determined the probabilities for various claim amounts for drivers aged 16 through 21. And here they are. So the amount of the claim. So 70% of the time, the 16 to 21-year-olds are making no claim at all. Then 15% of the time, they're making a $2,000 claim. 8% of the time, it's a $4,000 claim, and so on. And our job is to find the expected value and determine what that means in practical terms. So I'm going to grab the calculator. I'm going to go to Stat, Edit. I'm going to clear out these old columns, and I'm going to type in those new values for the variable, which will be 0, 2000, and so on. And then I'm going to type in the probabilities. So I'll be right back with that. There, they're all typed in. So now I go to Stat, Calculate, one variable, L1 and L2, just like always for a discrete random variable distribution. And I find that the mean is 1100. All right, so let me write that up. And there we have it. So because the expected value is 1100, that means that this auto insurance company expects any randomly selected 16 to 21-year-old driver to make a claim, an auto insurance claim, I guess I should say, an auto insurance claim of, and I should give it a unit. I mean, it's kind of obvious, but $1,100. So that will affect what the auto insurance company is going to charge, right? If it just wants to break even, which of course, what auto insurance company just wants to break even? They need to have profit to run. But if the company just wanted to break even, they would charge $1,100. So break even, they charge $1,100 to every 16 to 21-year-old driver who buys a policy. Right. But of course, if they want to make a profit, we make a note down here. If the company wants to make a profit, then they're going to have to charge more than $1,100. There, I just kind of put that in there for us. So if the company wants to make a profit, which hypothetically speaking they would want to, they're going to need to charge more than $1,100 to every single one of those drivers. That's how they determine insurance rates. I don't know if you knew that. That's also why you've noticed perhaps that 16 to 21, actually more like 16 to 25-year-olds get charged more for insurance. And then the older you get, the less they charge you. I'm going to stop right here, and then I'll see you back here for the next video on the next example.